Welcome back to Lesson 2, Part 2 on the development of the quantum theory. This lesson is part of the Unit 1 of Chemistry 12 on structure and properties of matter. Today we're going to examine the photoelectric effect, first observed by Heinrich Hertz in 1887. The diagram on the left shows an illustration of how when light strikes a metal, electrons can be ejected and current can be produced. This photoelectric effect was interpreted years later by Albert Einstein, shown here on the right hand side. So everything starts with the work of James Maxwell when he proposed that all electromagnetic waves consist of a series of wavelengths. So if we were to look at electromagnetic radiation, can consist of a mixture of gamma rays, ultraviolet, microwave, radio, and so on. This diagram shows clearly give you a picture in your brain to see what size those wavelengths are. So gamma rays are in the range of 10 to the minus 12 meters, whereas radio waves can be up to 1,000 meters, 10 to the 3. The other thing that is important to notice is the bar here below the diagrams that shows the frequency in hertz. The frequency ranges from 10 to the 20 to 10 to the 4th for radio waves and gamma rays. And the bar on the bottom part illustrates what would be the temperature of objects or wires in order for them to produce that type of radiation. So I show you here a range of 10 million Kelvin up to about 1 Kelvin here, for example, to produce from gamma rays to microwave. So as I say at the beginning of the lesson today, we're going to examine how light, when it strikes a piece of metal, can produce a current, as shown over here. This is a circuit. So in this circuit we have two pieces of metal, and electrons are going to be ejected when a specific light of a specific radiation frequency hits the piece of metal. So in order to see more in detail, let's watch the following video from YouTube that shows how
the photoelectric effect is the ejection of electrons from a surface when light of sufficient frequency shines on it. For example, when red light is directed at a metal surface, no electrons are ejected. However, when blue light, which has a higher frequency, is directed at the metal surface, electrons are ejected and a current flows through the wire as measured by the ammeter.
When blue light shines on the metal surface, electrons are knocked out of the metal. As long as light of sufficient frequency shines on the metal, free electrons are produced and current flows through the tube as measured by an ammeter. The current stops flowing when the light is turned off. When yellow light shines on the metal surface, electrons are knocked out of the metal. As long as light of sufficient frequency shines on the metal, free electrons are produced and a current flows through the tube as measured by an ammeter. The current stops flowing when the light is turned off.
So let's go over those important aspects of the photoelectric effect and come up with a series of major important points. First of all, we know that light of different colors would be able to eject electrons, but only a specific light. So for example, a red photon has a lower energy than a UV photon. And a photon energy must be transferred to the electron in order for the electron to be ejected. Electrons use some of this energy to break free from the atom, and some is left over as the electron's kinetic energy. It's also important to notice that the electron cannot break free from any atom unless enough energy is absorbed from the incoming photons, that is, a light of a specific wavelengths. Different atoms require different amounts of energy for their electrons to be removed. So this is expected when we use different metals. If we use the same source of light, it might be not the case that all the metals would eject electrons. The diagram below is to connect this concept of the photoelectric effect with what it actually happens in atoms of any sample of matter when they interact with light. So electrons can be occupying different energy levels, as shown here. The N1 to N5 refer to the energy levels. And when a quantum of energy is absorbed, the electron can be excited and transferred or transitioned to a higher energy level. then in that high energy level, the electron is not stable. So eventually it might drop down to a ground state. Let's say here the N1 state. So when we see those transitions from N5, for example, here shown in violet, to N1, is going to produce radiation of violet color that has a lot of energy. Whereas if we see a transition from N2 to N1, this is going to result in the electron giving off red light that has lesser amount of energy. How do we use an analogy to explain this photoelectric effect? So imagine if you consider that the electron is occupying those energy levels, or orbitals to be more precise, and those orbitals are caps. So they contain a specific amount of kinetic energy. They're moving around. These are for different types of metals: potassium, sodium, lithium. If we shine a red photon on these caps that contain the electron might get excited up to a certain level, but it's not going to leave the cap. It's not going to be ejected. However, if we use UV light that has much more energy, the electron will absorb the energy from that photon, and it might be ejected, resulting in the production of electricity. This work and the interpretation of the photoelectric effect was the reason why Albert Einstein was awarded the Nobel Prize in Physics in 1905. Thank you.